Okay, welcome to the next video in our regional circulations lesson. We're going to talk about the coronary arteries here and the circulation of the heart. Okay, first of all, you'll notice that AVO2 difference, as I pointed out in an earlier video, relatively high. So that means that your heart is consuming a great deal of the oxygen that it gets. Okay. And we say that the heart is underperfused. However, we know now that the heart's still getting enough oxygen. Okay, your body's just tuned to make sure that it gets it when it needs it. So your heart is very good at extracting the oxygen that it gets, so that when the oxygen enters the capillary beds, your heart can get it out. And the consumption is proportional to the cardiac work. So when demand is high, the percentage of cardiac output that the heart gets is high. Okay? So if I'm exercising, your heart gets plenty of blood. Okay? And your body is tuned to make sure that that happens. The local regulation is fairly exquisite, so that you will get vasodilation and your heart will get blood, at least if you're an ordinary human being, when you need it. Okay. The anaerobic capacity is small, which is another reason why you have to make sure that your heart gets enough blood, because it can't survive a lack of oxygen very well. It has to be able to respond to large increases in demand, because when that heart rate goes up, you're going to increase oxygen consumption quite a bit. The metabolic controls are more powerful than the neural controls. So by neural controls, we really mean the vasoconstriction that your autonomic nervous system elicits during the barrel reflex. So your autonomic nervous system will say, I need to get mean arterial pressure high. What it will do is it will constrict certain regions like your GI tract, which we'll find out in a minute, but it's not going to constrict the vasculature going to your heart. Okay, that would be bad. Why would you constrict blood flow to your heart at a time when your blood pressure is falling? No, you wouldn't want that. You want to make sure your blood gets enough oxygen to sustain itself and generate more work. So the metabolic controls are more powerful than the neural controls. That means when your heart starts to work harder, you're going to get vasodilation. And that will happen despite the fact that your barrel reflex is eliciting vasoconstriction in other areas of the body. Okay? Capillary reserve is large. That means there's collateral circulation, and there are collateral capillaries, and they'll open up when they need to, so that you'll get collateral circulation, let's say around an occlusion. Okay, so you'll get capillaries that will open up when you need to increase the flow to particular regions of the heart. And flow in the left coronary artery is maximal during diastole, okay? Unlike the situation in other beds and in the right coronary artery. So here is the aortic pressure. You get a nice increase in pressure during systole because you're shoving blood into the aorta, and then it declines. It goes down during diastole. And in your right coronary artery, it's a similar sort of profile, okay? The maximum is during systole, and then during diastole, you get a decline. But notice on the left, the maximum is during diastole, not during systole. And the reason why the profile is different is because your heart muscle is contracting, and it's contracting down upon the coronary arteries. So because the muscle is contracting and squeezing those arteries, it restricts flow during systole. And it kind of restricts it on the right side as well, but not nearly as much. Okay? So on the left side, the peak is actually during diastole, not during systole. This has consequences. If you increase the heart rate, what happens is that you reduce the period of diastole more than the period of systole. No matter what you do, your heart needs a certain amount of time to contract okay? And so what happens is when your heart rate goes up, both periods will be reduced, but the period of diastole will be more reduced than the period of systole. So What that means is that at higher heart rates, you might have a restriction on coronary flow on the left side. Now, note, this does not mean that your heart doesn't get enough oxygen when you exercise. It does. You get vasodilation and you'll get an increase in flow, and it's fine, okay? This is just a phenomenon that takes place that sort of limits that increase. And we point it out and we teach it because during heart disease, if you had heart disease on top of that increased heart rate, then it might have a significant effect, okay? So it is a special characteristic of the bed that might become significant during disease. It's always qualitatively there, but it doesn't really limit flow all that much in a normal human being. You'll still get an increase in flow when your heart needs it, okay? Don't tell me your heart doesn't get enough oxygen when you're exercising because the sympathetic nervous tone went up. Please don't tell me that. Your heart will get the oxygen that it needs, okay? All right, so having said that, let's look at our patient. Pulse rate 104, that's pretty high. And here is her echo. And you will note, you'll remember from previous lesson that the increased radius here in our dilated cardiomyopathy means that there's more wall tension. And that's not necessarily a bad thing if you've got a patient that has a heart disease, because increased wall tension means increased stretch on the cardiac muscle cells, and that means they'll contract with more force due to the Frank-Starling mechanism. However, the bad news when you have heart disease is that that increases the oxygen consumption, which means it increases the need for blood, okay? So that's one thing. The other problem is that the increased wall tension means you're squeezing those arteries more. And if you squeeze the arteries more, the radius goes down. If the radius goes down, the resistance to flow goes up, which means that this will tend to reduce the flow at a time when the metabolic demand is relatively high. So the increased wall tension has good and bad characteristics, okay? If you're squeezing those arteries, that's kind of a bad thing, okay? The other thing to note, although it may not be significant here, is that at least sometimes in patients with heart disease, you'll see an increase in wall thickness. That will reduce the coronary flow as well because you're squeezing those arteries more. With the more muscle you lay on, the more squeezing you do. And the more squeezing you do, the more you increase the resistance. And so that can make this into a relatively significant effect as well, okay? So there are pluses and minuses to all of this. All right. That's all I've got. Thank you for your attention, and when you're ready, we'll move on to the next video.